Have you ever played wall ball? That's a pretty weird question, especially in a physics lab. But it's important. Have you ever played wall ball and noticed that when you hit the ball at the wall, when it comes back slower? Have you ever wondered why this is? Today we'll be looking at 1D collisions. What happens when you roll a tennis ball at the wall? Overall, the physics principles involved in this will be momentum and the momentum principle. It will be the energy principle in collisions, specifically inelastic collisions, when there is no change in momentum but a change in energy. And then these equations can be represented where momentum is the multiplication of mass and velocity, the velocity update formula, the position update formula, and then the force of drag. Our video looks like this. The ball rolls at constant velocity towards a wall, and it hits the wall, comes back, decreasing in velocity until it comes to a stop. As it returns, it experiences constant deceleration. The results of the video is that it starts at approximately 0.01 meters. It hits the wall at 1.03 seconds, comes to a stop at 3.12 seconds, with an initial velocity recorded based on tracker data to be negative 1.3 meters per second, and the mass of the tennis ball is 0.056 kilograms. We then modeled this in GlowScript and then came to this graph that looks very similar to our last graph. As you can tell, it runs at constant velocity and then returns at a position in constant deceleration that incorporates friction and air resistance and drag. It then follows momentum for the new position. So how do we do that? Well, we set the mass to our values. We set the initial position and velocity, as well as the initial time step and the size of each time step. Then we set a conservation value to false, so that means that the initial momentum will stay. And then we set the drag constant to 0.035, which is similar to air resistance and friction on a ball on hard surface of wood. With these values, we then set the initial net force as equal to 0 because we had constant velocity. Then we updated the velocity and position based on this. This is before the ball came in contact with the wall. And then that was before time step equals 1.03, and we then set the initial velocity. Then, after the ball came in contact with the wall and the collision occurred, we then used the conservation of momentum using a Boolean statement, so that for all time steps after, we didn't have to redefine the momentum, but kept the momentum same as the negative momentum of the initial momentum. Then we set this to true. We also set the velocity based on our momentum principle. After that, we set the net force equal to drag air force as the ball came against resistance. We then updated the ball velocity and the position based on the net force. This was a constant net force, which means constant deceleration on the ball as it returned from the wall. Because of that, the velocity decreased and the position experienced an increase in an exponential form. The forces on the ball are as follows. Normal force goes up as gravity force goes down. That's why there's no change in y or z. However, there is a change in x from the forces. So how did we analyze this? Since it's an inelastic collision, that means that the ball maintains no change in momentum. The ball moved at a momentum that was equal to mass times velocity as it came closer to the wall. Then as it came back, it was negative mass times velocity. However, there was a decrease in kinetic energy. Because of that, as the ball returned, it eventually slowed down, since the ball loses kinetic energy when it hits the wall. Also, the friction and drag forces act on the ball, so that's why the ball came back in an exponential position versus time graph. It experienced constant deceleration and linear decreasing velocity. So how can we improve this lab? In future experiments, we can mess around with completely inelastic collisions or other inelastic collisions. We can also take into effect more than just friction and air resistance. We can take into effect changes in internal energy, thermal energy, and sound energy. We can also practice with 2D or 3D collisions and see what we learn from there. So overall, what does this mean? Now we understand what happens when a ball comes in contact with a stationary object and why it is slower as it returns. This is the example of a conservation of momentum in an inelastic collision, and what happens when there's a change in kinetic energy. We can also see how constant deceleration looks exponential for position versus time in a graph. And finally, we can recognize the impacts of the law of the conservation of momentum on the collision of a ball with a stationary wall.